Hello, and welcome to Starlit Science. Before we embark on today's cosmic journey, make sure to hit that like button and subscribe to join our ever-growing community of curious minds. And, as always, feel free to share where you're watching or listening from in the comments below, whether you're tuned in from the quietest corner of the Earth or perhaps from the heart of a bustling city. It's fascinating to think how we're all connected under the same stars. After all, no matter where you are, we're all stargazers at heart, bound by the same universe. Now let's turn our gaze to the heavens, quite literally. Have you ever wondered why stars, these magnificent beacons of light in the night sky, eventually burn out and die? What secrets do they hold, and how do they shape the universe around them? Today, we're diving deep into the life cycle of stars, from their dazzling birth to their inevitable end, unraveling the mysteries of what happens when their light fades. Stick with us as we explore the forces of gravity, nuclear fusion, and the incredible physics that dictate the rise and fall of these celestial giants. It's a story of creation, destruction, and everything in between, and trust me, you won't want to miss it. So, let's get started. Stars. They light up our skies, filling the night with their distant twinkle, and yet they are far more than just beautiful points of light. In fact, stars are some of the most fundamental and powerful forces in the universe. They shape galaxies, influence the birth of planets, and are the very engines of creation for the elements that make up the world around us. Without them, life as we know it simply would not exist. Understanding stars and their life cycles is not just a fascinating pursuit, it is essential for understanding the universe itself. The life of a star begins in vast cold clouds of gas and dust scattered across the cosmos. These molecular clouds, often called nebulae, are the nurseries of stars. Within these clouds, the dense regions of gas begin to collapse under their own gravity. As they do, the material at the centre starts to heat up, forming what is known as a protostar. Once the temperature is high enough, nuclear fusion begins, a process where hydrogen atoms fuse together to form helium, releasing an immense amount of energy in the process. This energy pushes outward, counterbalancing the inward pull of gravity, and the star is born. From this moment, a star enters what is called the main sequence phase of its life, a stage where it will spend most of its existence. During this time, the star maintains a delicate balance. Its core is hot and dense, constantly fusing hydrogen into helium, while its outer layers are held in place by the force of gravity. This equilibrium ensures the star shines brightly, providing light and heat to the space around it. But this balance is not permanent. Stars, like all things, are subject to change. As a star continues to burn through its nuclear fuel, the elements within it change. The hydrogen in its core gradually diminishes, and eventually fusion slows down. The balance between gravity and fusion is disrupted. The core contracts and heats up while the outer layers expand, transforming the star into a red giant. Now, not all stars follow the same path. The fate of a star depends largely on its mass. Low-mass stars, like our Sun, will eventually shed their outer layers to create a planetary nebula, leaving behind a dense core known as a white dwarf. These white dwarfs will slowly cool and fade over billions of years. For more massive stars, however, the end is much more dramatic. They explode in a supernova, a cataclysmic event that can outshine an entire galaxy for a brief time, scattering heavy elements like gold and uranium into space. What remains after a supernova can be either a neutron star or, if the star is massive enough, a black hole. The life and death of stars are deeply intertwined with the broader evolution of the universe. Stars are the factories that forge elements, everything from carbon to iron to the precious metals we value on Earth. These elements are spread across the cosmos when stars die, seeding the formation of new stars, planets, and even life itself. In this way, the death of one generation of stars becomes the foundation for the next. Now, this process of star formation, life, and death has been studied for centuries. Early thinkers like Fred Hoyle explored the idea of nucleosynthesis, the process by which stars create new elements through fusion. Hoyle's work laid the foundation for our modern understanding of stellar evolution. He even proposed that elements heavier than iron could only be created in the explosive deaths of stars, an insight that changed how scientists thought about the origins of elements in the universe. Later, astronomers like Matthias Steinmetz expanded upon these ideas with more refined models of star formation especially within galaxies. His work contributed to our understanding of how stars are born in the turbulent gas clouds of galactic disks, where conditions can vary widely, leading to different types of stars depending on the environment. While we have a solid grasp of the broad strokes of stellar life, there are still many mysteries surrounding the details of how stars live and die. For example, while we know that stars form from gas clouds, what exactly triggers that first collapse? Why do some stars die as white dwarfs, while others end up as black holes? And what happens to the material inside a black hole, where our current understanding of physics breaks down? These questions take us into realms of physics where the conventional rules of science begin to blur. Theories about black holes, quantum mechanics, and even the possibility of multiple universes challenge us to think beyond the known and into the speculative. While much of this is still a mystery, it's these same mysteries that drive scientists to push the boundaries of our knowledge. In the chapters that follow, we'll dive deeper into these topics, exploring the life cycle of stars in more detail and touching on the fascinating theories that continue to shape our understanding of these cosmic giants. From the science of stellar fusion to the mind-bending concepts of black holes and the multiverse, we'll unravel the truths and the theories that explain the rise and fall of stars. As we explore the cycles of birth and death in the universe, we'll see that stars are not just points of light in the night sky. They are the very engines of creation that have shaped everything we know and will continue to shape the universe long after we're gone. Stars, those shimmering beacons in the night sky, begin their journey in vast cold clouds of gas and dust scattered across the universe. These regions, known as molecular clouds or nebulae, are often referred to as the birthplaces of stars. They are dense regions of the cosmos filled with a mixture of hydrogen, helium and heavier elements, cooled to temperatures so low that the gas condenses into tiny particles. It's in these quiet, serene regions that the raw materials for stars are gathered. But what exactly triggers the birth of a star within one of these massive clouds? It's not a simple process, and it begins with something quite fundamental: gravity. Gravity is a force that attracts matter towards itself. In the vastness of space, even a small clump of gas or dust can begin to pull in more material. As more and more gas is drawn together, the clump becomes denser, and the force of gravity becomes stronger. This process of gravitational collapse starts to create a dense core in the center of the cloud, and as this core contracts, it heats up. Now, while gravity is the main player, some scientists suggest that there could be other factors at play, especially when we look at the universe on its grandest scales. For example, Lee Smolin, a theoretical physicist, has proposed an intriguing idea in his work on the cosmological constant. He suggests that quantum fluctuations in the early universe could have contributed to the formation of large-scale structures like galaxies and nebulae. These fluctuations are tiny, random changes in the energy of empty space, and though they may seem insignificant, over billions of years, they could have nudged matter into clumps that eventually became stars. In this way, the very fabric of space itself, influenced by these fluctuations, might have helped set the stage for the birth of stars. In addition to these cosmic quantum influences, the birth of stars might also be shaped by the state of matter itself. The Nobel Prize-winning physicist Murray Gell-Mann proposed the idea that stars might form in alternative states of matter, influenced by quantum effects. This means that rather than simply forming out of ordinary gas and dust, stars could emerge from more exotic forms of matter, shaped by the underlying quantum laws of the universe. While this is a speculative idea, it opens the door to the possibility that stars might not always form in the way we traditionally understand, and that some of the material that makes up a star could have been in a different state, one influenced by quantum mechanics. Once a dense enough core has formed and the temperature within the collapsing gas cloud rises to millions of degrees, something remarkable happens. The conditions are now right for nuclear fusion to begin. Nuclear fusion is the process by which hydrogen atoms collide and fuse together to form helium, releasing an immense amount of energy in the process. This energy is what powers the star, keeping it alive for billions of years. It's this energy from fusion that creates the light and heat we see from stars like our Sun. As fusion begins, the outward pressure from the energy produced counters the inward pull of gravity. This delicate balance is what defines a star in its early stages. The star, now known as a protostar, is in the process of stabilizing. The material in the outer layers is still falling inward, while the core is hot enough to keep the fusion reactions going. Over time, the protostar continues to shrink and heat up, and the fusion reactions become more efficient, gradually turning the young protostar into a full-fledged star. Once this balance between gravity and fusion is achieved, the star enters what is known as the main sequence phase of its life, a phase that can last for billions of years. But before that stability is reached, there are a few more nuances to consider in the star's birth. The first thing to note is that the process of star formation doesn't happen in isolation. A single star is often born within a star cluster, a group of stars that formed from the same molecular cloud. These clusters can range from just a handful of stars to thousands, and they can exert gravitational forces on one another, influencing their formation. The energy from one star's formation can trigger the collapse of other regions of the cloud, leading to the birth of multiple stars in a sort of cosmic chain reaction. It's a process that unfolds over millions of years, though the exact details can vary depending on the conditions within the molecular cloud. What's particularly interesting is that not all stars are born the same. The mass of a star plays a crucial role in determining its eventual fate. High-mass stars, for example, are born from the densest regions of molecular clouds and burn through their fuel much faster than low-mass stars. This means they live fast and die young, with lifespans measured in just a few million years, compared to the billions of years a low-mass star like our Sun might enjoy. The initial conditions of the gas cloud, including its density and temperature, help determine whether a star will be massive or more modest in size. The birth of a star is also a reminder of the vast forces at work in the universe. The energy released during star formation is immense, and as a star forms, it often emits large amounts of radiation, heating up the surrounding gas and dust. In some cases, this radiation can cause nearby material to evaporate, preventing further star formation in the area. This interaction between a forming star and its environment plays a role in shaping the star's development, and in some cases, it can even prevent other stars from forming nearby, creating what's known as a star-forming region. While the science behind star formation is well understood in many ways, the process is still a subject of intense study, and there's much that we don't yet fully grasp. For example, while we know that gravity drives the initial collapse of the gas cloud, there are still questions about exactly how the collapse happens. How do molecular clouds, which can be enormous and diffuse, collapse in a controlled way to form stable stars? What are the finer details of how quantum effects might influence star formation? These are questions that scientists like Lee Smolin and Murray Gell-Mann have begun to explore in their work, and they continue to open up new avenues of thought. The birth of a star is not just a scientific curiosity, it's a fundamental process that shapes the universe. The energy released during star formation ignites the cosmos, giving rise to galaxies, solar systems, and eventually, life itself. It's a process that spans millions of years, but in the grand scale of the universe, it happens continually, shaping and reshaping the very fabric of space. And while we have a solid understanding of how stars form, the journey from gas cloud to shining star still holds many mysteries, waiting for the next generation of scientists to uncover. The heart of every star, from the smallest red dwarf to the most massive supergiant, is powered by the process of nuclear fusion. It's this process that allows stars to shine so brightly and release the enormous amounts of energy we see as light and heat. At its core, nuclear fusion is relatively simple. It's the process by which lighter elements fuse together to form heavier ones, releasing energy in the process. In stars, the most common fusion reaction is the conversion of hydrogen into helium. Hydrogen, the lightest and most abundant element in the universe, consists of a single proton and a single electron. When the temperature and pressure in the core of a star become high enough, typically millions of degrees, the hydrogen atoms start to move so quickly that they collide with each other at extremely high speeds. Under these conditions, the force of the collisions is strong enough to overcome the electrostatic repulsion between the positively charged protons. When this happens, the protons fuse together to form a helium nucleus, which consists of 2 protons and 2 neutrons. During this process, energy is released in the form of gamma rays. This energy radiates outward from the core of the star and counterbalances the force of gravity trying to collapse the star. It's this delicate balance between the outward pressure from fusion and the inward pull of gravity that keeps a star stable for billions of years. The process of hydrogen fusion releases so much energy that it creates the intense heat and light we associate with stars. In fact, this fusion process is the reason our Sun, a relatively small star, has been shining for about 4.5 billion years, and it will continue to do so for another few billion years. But what if there's more to the story? What if the interiors of stars are not made entirely of the simple, familiar matter we think of? This is where theories of more exotic forms of matter come into play, ideas that challenge the conventional understanding of stellar interiors. Some researchers, like J.R. Gott and Giorgio Parisi, have proposed the concept of strange matter. Strange matter is a theoretical form of matter that could exist in the cores of stars, where extreme pressures and temperatures might cause protons and neutrons to behave differently than they do in ordinary matter. In strange matter, the subatomic particles may form what are called strange quarks, in addition to the usual up and down quarks that make up protons and neutrons. This idea, while still speculative, suggests that in the densest regions of a star, such as the core of a massive star nearing the end of its life, the normal rules of matter might not apply. If strange matter does exist, it could help explain certain extreme behaviors observed in stars, particularly those in their final stages of life. These are the types of ideas that may one day challenge our fundamental understanding of the state of matter in the universe. And it's not just strange matter that could play a role in stellar interiors. Quantum effects, those mysterious phenomena that govern the behavior of particles on the smaller scales, could also have a profound impact on how stars form and evolve. The uncertainty principle, first articulated by the physicist Werner Heisenberg in the early 20th century, is one of the most famous principles in quantum mechanics. The uncertainty principle states that the more precisely we measure one property of a particle, like its position, the less precisely we can measure its momentum. In the context of stars, this principle can have important implications for the behavior of particles inside the star. At the extreme densities and temperatures found in a star's core, the uncertainty principle could influence the way particles interact with one another, potentially affecting the rate of fusion or the way energy is transported within the star. This interplay between quantum mechanics and stellar fusion is an area of active research, and while we're far from fully understanding all the effects, it's clear that quantum principles could shape the inner workings of stars in ways we're only beginning to grasp. The fusion of hydrogen into helium might seem like a straightforward process on the surface, but the underlying quantum effects are anything but simple. One of the most exciting and perhaps speculative ideas in the study of stars comes from physicist Andre Linde. Linde is known for his work on the theory of inflation, which posits that the early universe underwent an extremely rapid expansion just moments after the Big Bang. But Linde's ideas go even further, suggesting that the quantum fluctuations we observe in space could play a role in shaping not just stars, but entire universes. According to his theories, these fluctuations could cause the formation of pocket universes within the larger multiverse, with each pocket potentially having different physical laws. Could stars themselves be influenced by such cosmic-scale quantum effects? Could the formation of stars and their ultimate deaths be tied to processes on a much grander cosmological scale? Though Linde's multiverse theories remain speculative, they open up the possibility that the formation of stars could be more complex than simply the gravitational collapse of gas clouds. If quantum fluctuations are involved in the formation of stars, it could mean that stars don't form in a purely deterministic way. Instead, the conditions of the universe, both large and small, could influence the exact path that stars take from birth to death, shaping the very fabric of the cosmos itself. As we consider these high-level ideas about the nature of stellar matter and the role of quantum effects, it's important to keep in mind that much of this is still speculative. The concept of strange matter, the influence of quantum fluctuations on star formation, and even the idea of a multiverse are all cutting-edge theories that push the boundaries of our understanding. While they are exciting avenues of research, they remain unproven, and we must continue to rely on well-established science to guide our understanding of how stars work. The core process of nuclear fusion, where hydrogen fuses into helium, remains the cornerstone of how stars shine. It's a process that powers not just stars but the entire cycle of life in the universe. As stars form, they forge the elements that make up planets, life, and even ourselves. But the more we learn about the quantum and exotic matter that might be at play within stars, the more we realize that there is still so much to discover. Each new theory, no matter how speculative, brings us closer to a deeper understanding of the universe and our place in it. In the end, the fusion that occurs in the core of stars is more than just the mechanism that powers their light. It is the process by which stars give birth to the elements that will go on to form new stars, planets, and potentially life. As we continue to explore the unknowns of quantum physics and exotic matter, we may find that stars themselves are far more mysterious than we ever imagined. The life of a star is a delicate balancing act between two opposing forces, gravity and nuclear fusion. These forces work together in harmony, creating what we call the main sequence phase of a star's life. It's during this phase that a star achieves a kind of stability, one that can last for billions of years. Gravity pulls the star's material inward, while the energy released from nuclear fusion pushes outward, creating a perfect equilibrium that keeps the star stable. At the heart of this process is nuclear fusion, where hydrogen atoms are fused into helium, releasing enormous amounts of energy. This energy is what powers the star and causes it to shine. The outward pressure from this energy is constantly fighting against the inward pull of gravity, which wants to collapse the star in on itself. For most stars, this balance holds steady, and they remain in the main sequence phase for the majority of their lives. The main sequence phase is not a brief moment in a star's existence, but rather the longest and most stable part of its life cycle. For stars like our Sun, this phase can last for about 10 billion years. The star spends this time steadily burning through its hydrogen fuel in the core, creating helium and releasing energy. As long as the fusion process continues, the star will maintain its size and luminosity, and the forces within the star will remain balanced. But this balance is fragile, and it is only sustained for as long as the star has fuel to burn. During this phase, the star undergoes relatively little change. Its outer layers remain stable, and the core's temperature and pressure stay constant. But even within this stability, there are subtle, often imperceptible changes. The rate at which fusion occurs in the core gradually decreases over time as the hydrogen is consumed. As a result, the star begins to lose its balance, and it will eventually evolve into a new phase of its life. But that's a long way off for most stars in the main sequence. It's in the heart of this stability that physicists like Roger Penrose have raised intriguing ideas about the relationship between entropy and the cyclical nature of the universe. Penrose's work suggests that the universe itself might be caught in a cycle of birth, evolution, and eventual decay, a cycle in which stars play a crucial role. The entropy of a star, or the measure of disorder within its system, is tied to this cosmic cycle. As a star burns through its fuel and undergoes nuclear fusion, it creates new, more complex structures. But eventually the star will reach the end of its fuel supply and entropy will increase as it collapses or explodes. This process of increasing entropy may be tied to the larger fate of the universe itself, suggesting that the life and death of stars are connected to the ultimate fate of all things. As we think about the forces that govern a star's life, we also come to realize how little we still understand about the finer details of this balance. Roger Angell, a leading researcher in astrophysical optics, has explored how the delicate balance of forces within a star could be linked to the detection of gravitational waves in unstable stellar configurations. Gravitational waves are ripples in space-time caused by massive objects moving through space, and their detection has opened up a new window into the universe. While we often think of gravitational waves as originating from the collision of black holes or neutron stars, Angell's work suggests that even within a seemingly stable star, the forces at play might be capable of generating these ripples, especially in more extreme stellar environments. This brings us to the idea that even the most stable stars might not be as stable as they seem. The forces that maintain equilibrium within a star are incredibly delicate, and small changes can have large effects. In extreme environments, such as in the cores of stars with much higher masses than our Sun, this balance can be easily disrupted. When a star burns through its hydrogen and begins to fuse heavier elements, the core contracts and heats up, while the outer layers expand. This changes the balance of forces, potentially leading to instability. In some cases, this disruption can trigger a violent event, like a supernova, where the star violently collapses or explodes, scattering its material across space. Even more subtly, a star might experience oscillations in its internal structure, known as stellar pulsations. These oscillations happen when the balance between gravity and fusion is temporarily disturbed. As the outer layers of the star expand and contract, they cause variations in the star's brightness and energy output. These pulsations may be small, but they are a reminder that even in the most seemingly stable stars, there is a constant dance between order and chaos. Over time, these oscillations can cause significant changes in the star's structure, leading to its eventual transformation into a new stage of its life. While these ideas about instability and chaos in stars are fascinating, it's important to remember that most stars spend the majority of their lives in a remarkably stable state. The energy produced in their cores is constantly balancing the inward pull of gravity, creating a dynamic equilibrium that sustains the star for billions of years. This phase of stability is crucial for the development of life in the universe, as stars provide the necessary conditions for planets to form and life to emerge. However, as stars age, the delicate balance that sustains them begins to shift. Eventually, the fuel in the core will be exhausted, and the star will move on to its next phase. For low-mass stars like our Sun, this means expanding into a red giant, while for more massive stars, it could lead to a supernova explosion. These later stages are marked by instability and chaos, but they also set the stage for new creations in the cosmos. When a star explodes in a supernova, it scatters heavy elements across the universe, enriching the interstellar medium and providing the building blocks for new stars, planets, and even life. It is within the apparent stability of the main sequence phase that we see the paradox of stellar life. Even in moments of calm, there are subtle shifts and underlying complexities at play. While stars seem to remain constant, they are constantly evolving, influenced by the intricate balance of forces within them. And as we look deeper into these forces, gravitational, nuclear, and even quantum in nature, we begin to realize that what we perceive as stability is just a temporary phase in a much larger and more dynamic process, one that will continue to unfold over the vast timescales of the universe. The main sequence is but one chapter in the long life of a star, but it's the phase where stars truly come to life, providing the light and energy that sustain the universe. As stars age and deplete the hydrogen in their cores, they undergo a remarkable transformation. This marks the beginning of the red giant phase, a time when a star expands dramatically, growing much larger and cooler than it was during its main sequence life. The red giant is a star in transition, still burning fuel, but now fusing heavier elements in its core and experiencing changes in its outer layers. During this phase, the core of the star contracts under gravity, while the outer layers expand, causing the star's outer shell to cool and turn red. The energy output remains high, but the temperature of the outer layers drops significantly, shifting the star's color from the brilliant yellow or white of the main sequence to a much cooler red. For stars like our Sun, the red giant phase represents a period of swelling as the star expands to many times its original size, potentially engulfing nearby planets, or even affecting the orbits of those further away. But this expansion isn't simply a result of the star running out of hydrogen. As the core contracts and heats up, it begins to fuse heavier elements such as helium. This process releases additional energy, which in turn pushes against the star's outer layers, causing them to expand further. At this stage, the star is effectively running on a kind of fusion ladder, using increasingly heavier elements as fuel, from helium to carbon and oxygen. The fusion of these elements brings about complex changes in the star's structure, and the interaction between these processes results in the red giant's dramatic transformation. While the core fuses elements like helium, the outer layers begin to experience new forces. The energy from fusion pushes outward, but gravity is still trying to collapse the star. The result is a tug-of-war between these opposing forces, which is partly responsible for the changes in the star's appearance and behavior. The outer layers of the red giant become unstable, and the star may exhibit signs of pulsation, where its brightness fluctuates over time. These variations are subtle but significant, suggesting that even within the apparent stability of the red giant phase, there are underlying forces at play that we don't fully understand. One of the key aspects of stellar evolution at this stage is the magnetic field of the star. Magnetic fields are crucial in the life of a star, especially as it moves into the red giant phase. Jocelyn Bell Burnell, best known for her discovery of pulsars, made important contributions to the study of neutron stars and the magnetic fields associated with them. Her work highlighted the role that magnetic fields play in the behavior of stars, particularly when they are in extreme states like those found in red giants. Neutron stars, the remnants of massive stars, have incredibly strong magnetic fields. These fields can cause dramatic changes in the way a star behaves, and understanding these effects in neutron stars has led to a broader understanding of how magnetic fields influence stars in other phases of their lives, including red giants. While neutron stars and red giants are at opposite ends of the stellar life cycle, the role of magnetic fields in both types of stars is undeniably important. As a star enters the red giant phase, its magnetic field can interact with the surrounding plasma, the hot ionized gas that makes up the star's outer layers. This interaction can create powerful stellar winds, which are streams of particles flowing away from the star. These winds are responsible for carrying away material from the star, and they play a key role in the star's eventual evolution. In some cases, the interaction between the star's magnetic field and its plasma can lead to unusual behaviors. For example, the magnetic field might channel the stellar wind in certain directions, creating patterns of emissions or causing material to be expelled more violently. This can affect the star's mass loss over time, altering the path the star will take toward its eventual end. The magnetic field's influence also extends to the star's rate of rotation, which can slow down as the star loses mass through these powerful winds. Another important figure in the study of stellar magnetic fields is Alessandro Patruno, an astrophysicist who has investigated the role of magnetic fields in the late stages of stellar evolution, particularly in high-mass stars. His work has shown that in high-mass stars, magnetic fields can lead to significant changes in the way the star behaves as it evolves. In the case of red giants, these magnetic fields might be responsible for the complex dynamics in the star's outer layers, contributing to both the star's growth and eventual shedding of mass. This research suggests that the magnetic fields at work in red giants might not only influence the star's behavior, but could also provide clues to the larger-scale processes that govern stellar evolution. While magnetic fields are crucial in shaping the behavior of red giants, there is also another force at play: stellar winds. These winds are driven by the intense energy produced by the star's core, which causes the outer layers of the star to expand. As the star ages, the material in these outer layers becomes increasingly unstable and is blown away by the energy produced in the core. The result is a steady outflow of particles into space, which can have a significant impact on the star's surroundings. Stellar winds are not just a feature of red giants. All stars experience them to some degree, but in the case of red giants, these winds are especially intense. As the star continues to expand, the outer layers become cooler and more diffuse, and the wind speed increases. The mass loss due to these winds can be quite dramatic, with a star like our Sun potentially losing up to 10% of its mass in the form of stellar wind during its red giant phase. The loss of mass due to stellar winds is one of the factors that will determine how a star ultimately evolves. For low to medium mass stars, the loss of mass during the red giant phase can lead to the creation of a planetary nebula, which is a shell of ionized gas and dust that is expelled by the star. The remaining core becomes a white dwarf, a dense, cooling remnant of the star. In contrast, more massive stars, which have stronger magnetic fields and more intense stellar winds, can undergo much more dramatic transformations, eventually leading to a supernova explosion. The red giant phase is an important stage in a star's evolution, as it marks the transition from the fusion of hydrogen to the fusion of heavier elements, but it's also a time when the star becomes increasingly unstable, as the balance between gravity, fusion, and other forces like magnetic fields and stellar winds begins to shift. These forces are responsible for the changes in the star's structure and appearance, and they will ultimately determine the star's fate. In the case of high-mass stars, the red giant phase is a precursor to even more dramatic events, such as a supernova explosion. This explosion, triggered by the collapse of the star's core, is one of the most powerful events in the universe, and it has the potential to outshine an entire galaxy. The material expelled during a supernova will eventually form new stars, planets, and other cosmic objects, continuing the cycle of stellar birth and death. The red giant phase is a time of both expansion and decay, a time when the star's core is hot and dense, fusing heavier elements, while its outer layers are cooling and being blown away by powerful winds. The magnetic fields, stellar winds, and gravitational effects all contribute to the star's transformation, leading it toward its ultimate fate. While the red giant phase can last for millions to billions of years, it is only a brief moment in the life of a star. However, it is a crucial one, as it sets the stage for the next chapter in the star's life and ultimately its death. When a low-mass star reaches the end of its life, it undergoes a quieter, less dramatic process compared to its more massive counterparts. Rather than exploding as a supernova, as a massive star might, a low-mass star gently sheds its outer layers and becomes a white dwarf, a dense, cooling remnant of the star's former self. These stars, with masses up to about 8 times that of our Sun, have spent billions of years fusing hydrogen into helium at their cores. As they run out of fuel, their nuclear reactions slow down, and they can no longer support their outer layers against the inward pull of gravity. What follows is a gradual shedding of the outer layers, leaving behind the hot, dense core. This core, now a white dwarf, is composed primarily of carbon and oxygen. At first, white dwarfs are incredibly hot, with surface temperatures that can exceed 100,000 degrees Celsius, but over time, they begin to cool, losing energy at a gradual pace. This cooling process will continue for billions of years, eventually leading the white dwarf to fade into the cold darkness of space. The fascinating thing about white dwarfs is that their size is surprisingly small. Despite having a mass similar to that of our Sun, they're only about the size of Earth. This is due to the immense gravitational pressure that causes the star's material to become incredibly dense. But while the physics of white dwarf formation is well understood, there are still many unanswered questions about their long-term behavior, especially when we begin to consider more speculative and mysterious factors like dark matter. Dark matter, the invisible and elusive substance that makes up about 25% of the universe's mass-energy content, is a key player in many cosmic phenomena, but its exact nature remains one of the greatest mysteries in astrophysics. Scientists like Jim Peebles and Simon White have explored how dark matter could be connected to the evolution of stars, including white dwarfs. While dark matter doesn't interact with ordinary matter through electromagnetism and thus doesn't produce light, it does exert gravitational influence, which is why it's detectable through its effects on galaxies and galaxy clusters. The intriguing question is, could dark matter have an effect on white dwarfs? Could it be involved in the way these stars cool down? While the idea is speculative, there is growing interest in the possibility that dark matter could interact with white dwarfs in subtle ways, affecting their cooling process. In particular, some researchers suggest that dark matter might be able to deposit energy into a white dwarf, influencing how quickly it cools and even potentially delaying the cooling process. This could mean that white dwarfs remain hot for much longer than we currently expect, adding complexity to our understanding of their life cycle. This suggestion builds on earlier work by Lars A. Borg, a scientist whose research has highlighted potential interactions between white dwarfs and dark matter that could make these stars behave in unexpected ways. Borg has proposed that white dwarfs may not be as stable as once thought, and that dark matter could be responsible for sudden transformations in their internal structure. According to this theory, if a white dwarf were to accumulate enough dark matter, it could alter its internal dynamics, potentially causing the star to collapse in a manner that is not typical for a white dwarf. This could lead to dramatic changes in the star's behavior or even trigger a new type of stellar event that we have not yet observed. The idea that dark matter could influence a white dwarf in such a profound way adds an intriguing layer of complexity to our understanding of stellar evolution. If dark matter does play a role in the cooling process or the stability of white dwarfs, it could have implications for the study of other types of stellar remnants as well. It could also help explain some of the mysteries surrounding the behavior of other celestial objects such as neutron stars and how they interact with dark matter. While the interaction between dark matter and white dwarfs remains speculative, it connects to much larger cosmic scale mysteries. Dark matter is one of the universe's most pervasive and enigmatic components, and it has a significant influence on the structure and behavior of galaxies. The role that dark matter might play in stellar remnants like white dwarfs adds another layer of mystery to the study of the universe. As scientists continue to explore the invisible forces at work in the cosmos, the connection between dark matter and white dwarfs could provide crucial insights into both stellar evolution and the nature of dark matter itself. Even more fascinating is the possibility that white dwarfs might not be the final stage of a low-mass star's life, as we once thought. If dark matter does influence the cooling and stability of white dwarfs, it could open the door to new types of stellar transformations that we are only beginning to comprehend. Perhaps these stars could evolve in ways that are not yet on our radar, with dark matter playing a role in their behavior in ways that go beyond what we currently understand. This idea also ties into the broader quest for understanding the invisible elements of the universe, dark matter and dark energy. These substances, which together make up about 95% of the total energy content of the universe, are far more mysterious than anything we can see. Our understanding of how these forces shape the universe is still in its infancy, and the potential role of dark matter in the cooling and evolution of white dwarfs is just one example of how this elusive substance might influence the life cycle of stars. The mystery of dark matter and its interactions with stars is just one facet of the larger cosmic puzzle. As our understanding of white dwarfs and dark matter evolves, it could lead to groundbreaking discoveries that reshape our ideas about the universe. If dark matter is indeed affecting the cooling of white dwarfs, we might be able to measure these effects and use them to better understand not only white dwarfs, but the very nature of dark matter itself. For now, the cooling process of white dwarfs remains a well-understood but still imperfectly measured phenomenon. We know that these stars will continue to cool over billions of years, eventually becoming black dwarfs, objects so cold that they no longer emit any significant radiation. Yet, the question of whether dark matter has a role to play in this cooling process is one that could define the future of astrophysics. As we continue to explore the mysteries of the universe, the fate of low-mass stars and their evolution into white dwarfs will undoubtedly remain a central topic of study. Whether or not dark matter is involved, the journey of a white dwarf from a glowing ember to a cold, dark remnant is a fascinating story that reflects the ongoing transformations of the cosmos. When a high-mass star reaches the end of its life, it undergoes one of the most dramatic and awe-inspiring events in the universe, the supernova. This is not merely the death of a star, but a spectacular explosion that can outshine an entire galaxy for a brief period, releasing more energy than our Sun will during its entire lifetime. The death of a high-mass star marks the violent conclusion of a stellar life cycle, one that begins with the fusion of lighter elements in the core and ends with the creation of heavier elements through the intense pressures and temperatures that exist in the star's final moments. A high-mass star burns through its nuclear fuel much more rapidly than a low-mass star like our Sun. Over the course of millions of years, it fuses hydrogen into helium, and then, once the hydrogen in the core is exhausted, it begins to fuse heavier elements, such as helium into carbon, and then carbon into oxygen, neon, and silicon. As the star's core contracts and becomes denser, the outer layers expand, and the star transforms into a supergiant. This process continues until the core is primarily made of iron, an element that cannot undergo fusion to release energy. At this stage, the star has reached a critical point. Iron is the heaviest element that can be formed through fusion in the core of a star, but it does not provide the necessary energy to support the star against the pull of gravity. When the core of the star becomes predominantly iron, fusion stops, and the core collapses under its own immense gravity. This rapid collapse results in an enormous explosion, a supernova, which can release as much energy as the Sun will emit in its entire lifetime in just a few seconds. But what is happening in these final moments of collapse? The core of the star, now incredibly dense, undergoes a process where protons and electrons combine to form neutrons, creating a neutron star. The outer layers of the star are blown away in a violent explosion, sending shock waves into space. During this explosion, the intense heat and pressure allow the fusion of even heavier elements, such as gold, platinum, and uranium, which are scattered into the surrounding space. This process of stellar death is responsible for creating many of the heavy elements found on Earth and in other planets, making supernovae not just destructive events, but also essential for the creation of the building blocks of life. As we observe these extraordinary events, we also start to delve into deeper, more speculative aspects of their nature. Stephen Hawking's work in quantum cosmology offers some fascinating insights into the very fabric of space-time. Hawking proposed that quantum fluctuations, tiny changes in energy at very small scales, might play a role in shaping the outcome of these cataclysmic events. In the case of a collapsing star, these fluctuations could contribute to disturbances in space-time, creating ripples that propagate outward as gravitational waves. Gravitational waves, which were first predicted by Albert Einstein and later confirmed by direct observation, are ripples in the fabric of space-time itself. They are caused by the acceleration of massive objects such as the collapse of a star. These gravitational waves, which are now detectable thanks to advanced instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, offer a unique window into some of the most extreme and distant events in the universe. The detection of gravitational waves from supernovae and other stellar events can provide critical insights into the mechanics of these explosions and the nature of the matter inside them. In this sense, supernovae are not just spectacular explosions, but they also offer a way to study the very nature of space-time and how the universe evolves. While supernovae are fascinating in their own right, they also play a crucial role in the creation of black holes. When a star with a mass greater than about 25 times that of the Sun undergoes a supernova, the collapse of its core is so intense that it can lead to the formation of a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are mysterious objects, their event horizons marking the point beyond which we cannot see or know what happens. They are a natural consequence of the intense forces at work during a supernova, and they continue to be one of the most intriguing objects in astrophysics. Kip Thorne, a Nobel laureate and expert in gravitational physics, has explored how black holes and supernovae can be linked through gravitational wave emissions. Thorne's work suggests that when a supernova occurs, the resulting gravitational waves carry valuable information about the collapse of the star and the formation of the black hole. By studying these waves, scientists can learn more about the structure of black holes, the behavior of matter in extreme conditions, and even test the predictions of Einstein's theory of general relativity. Gravitational waves could therefore be the key to unlocking many of the mysteries surrounding stellar deaths and black holes. But the implications of these events go beyond just the formation of black holes or neutron stars. The collapse of matter in a supernova and the subsequent formation of a black hole may represent the very end of space-time itself. Lee Smolin, a theoretical physicist, has suggested that the process of a star collapsing into a black hole might not just lead to a singularity, an infinitely dense point in space, but could actually cause a breakdown of the laws of physics as we understand them. In his speculative theory, the collapse of matter into a black hole could mark the end of the current space-time framework and the beginning of a new one. Smolin proposes that black holes might be the gateways to new universes, where the laws of physics are different and the entire structure of space-time is fundamentally altered. This idea challenges our conventional understanding of space-time, suggesting that instead of being a one-way journey into a singularity, the collapse of matter could be a doorway to a new reality. Such theories, though highly speculative, are exciting because they force us to rethink the very nature of the universe and how stars, black holes, and even the fabric of space-time itself are interconnected. The death of a high-mass star is no longer just an ending, but a potential beginning, an event that could ripple through the fabric of the cosmos, shaping the future of everything that follows. As we explore the end of a star's life, we are forced to confront not just the physical processes that occur during a supernova, but the deeper questions about the very structure of the universe. The birth of black holes, the emission of gravitational waves, and the speculative role of these events in shaping new universes offer a tantalizing glimpse into the future of astrophysics. In the coming decades, as technology improves and our understanding of these phenomena deepens, we may find that supernovae and black holes are not just markers of the end of a star's life, but also keys to understanding the fundamental nature of the cosmos itself. For now, as we observe the violent deaths of stars, we are reminded of the incredible forces at work in the universe, forces that shape galaxies, create new elements, and perhaps even give birth to new realms of existence. The study of these events not only helps us understand the death of stars, but it also brings us closer to answering some of the most profound questions about the universe and our place within it. Through the study of supernovae, gravitational waves, and black holes, we are uncovering the deepest mysteries of the cosmos, and with each discovery, we take one step closer to understanding the true nature of space, time, and the universe itself. When a massive star reaches the end of its life, it undergoes a dramatic collapse, forming one of the most fascinating and dense objects in the universe, a neutron star. Neutron stars are the remnants of stars that have gone through a supernova explosion, the violent death throes of a high-mass star. These remnants are incredibly dense, with a mass that can be up to 2 times that of our Sun, but packed into a sphere with a radius of only about 10 kilometers. To put this in perspective, if you could somehow compress the entire mass of the Earth into the size of a teaspoon, you'd have something about as dense as a neutron star. This immense density is the result of the collapse of the star's core. During the supernova, the core contracts under gravity, and the pressure becomes so extreme that protons and electrons combine to form neutrons, the particles that make up the heart of the star. As a result, a neutron star is made almost entirely of neutrons, packed together in a state of matter that's unlike anything we encounter on Earth. The density is so high that a single cubic centimetre of a neutron star could weigh about 400 million tons, far more than the mass of the entire human population combined. One of the most remarkable features of neutron stars is their powerful magnetic fields. These magnetic fields are incredibly strong, far stronger than anything we can produce on Earth. The strength of a neutron star's magnetic field is one of the reasons these objects are so intriguing. When a star collapses into a neutron star, its magnetic field is compressed along with its mass, leading to fields that are billions of times stronger than the magnetic field of Earth. These intense magnetic fields affect the behavior of the neutron star, influencing everything from the way it emits radiation to how it interacts with its surroundings. The importance of neutron stars extends beyond their fascinating physical properties. Hermann Bondi, a physicist who made significant contributions to the study of the early universe, suggested that neutron stars could provide important clues about the conditions of the universe just after the Big Bang. In his work, Bondi explored the idea that neutron stars might serve as indicators of the state of the universe in its infancy. The extreme conditions inside a neutron star, such as the pressure, density, and temperature, might reflect the conditions that existed in the early universe, giving scientists a unique window into the very beginning of space and time. Neutron stars also have a critical role in our understanding of galaxies. Vera Rubin, a pioneering astronomer, is famous for her work on the rotation curves of galaxies. She discovered that the outer regions of galaxies were rotating much faster than expected based on the visible matter alone, a finding that led to the theory of dark matter. Rubin's observations showed that galaxies had far more mass than could be seen in the form of stars and gas. Neutron stars, as one of the dense objects in galaxies, may contribute to the gravitational anomalies that Rubin observed, particularly in terms of their role in galactic dynamics. The mass and gravitational influence of neutron stars, although small compared to the overall mass of a galaxy, could still play a role in shaping how galaxies rotate and evolve over time. One of the most fascinating aspects of neutron stars is their behavior as pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky like a lighthouse beam, and as the pulsar rotates, we see flashes of radiation at regular intervals. Pulsars can spin incredibly fast, with some rotating hundreds of times per second. The discovery of pulsars was groundbreaking, as it provided the first direct evidence of neutron stars and opened up a whole new field of study in astrophysics. The phenomenon of pulsars has intrigued scientists for decades, and their study has led to insights into the behavior of matter under extreme conditions. One of the most important ideas in understanding pulsars comes from the work of Alexei Starobinsky, a theoretical physicist who has made significant contributions to the field of quantum gravity. Starobinsky's theories suggest that the behavior of pulsars could be explained through high-energy physics, particularly the idea that quantum gravity might influence the way matter behaves inside a neutron star. Quantum gravity, which seeks to unify quantum mechanics and general relativity, is a key area of research in modern physics, and its implications for neutron stars and pulsars are still being explored. Starobinsky's work on quantum gravity suggests that the extreme conditions inside a neutron star might be governed by quantum effects, leading to behaviors that are not fully explained by classical physics. For example, the way that matter behaves in the core of a neutron star, where neutrons are packed together so tightly, might involve quantum processes that could explain the star's rotation, its magnetic field, and its emission of radiation. By studying pulsars and their behavior, scientists hope to gain a deeper understanding of the fundamental laws of physics, particularly how quantum effects operate in the presence of intense gravitational fields. While pulsars have been studied extensively, they also challenge our understanding of the universe in profound ways. The extreme conditions in neutron stars and the role that quantum effects might play point to deeper mysteries that we have yet to fully understand. How do these extreme states of matter behave? What role does quantum gravity play in shaping the behavior of matter under such intense pressure and density? These questions remain at the forefront of astrophysical research, and could lead to groundbreaking discoveries that fundamentally alter our understanding of the universe. Neutron stars and pulsars also serve as powerful laboratories for testing the laws of physics. Because they are so dense and compact, they create environments where gravity and quantum mechanics are both at play in ways that cannot be recreated on Earth. The study of neutron stars allows scientists to test the predictions of general relativity in an environment where gravity is extraordinarily strong. It also provides a unique opportunity to study how matter behaves under conditions that are far beyond what we can simulate in laboratories. These stars challenge our current understanding of physics, and in many ways they offer clues about the future direction of astrophysics. The mysteries of neutron stars, pulsars, and quantum gravity remain largely unsolved. These remnants of dead stars, with their extreme densities, magnetic fields, and strange behaviors, continue to captivate scientists and lay the groundwork for future research. As we study these objects, we not only gain insights into the life cycle of stars, but also into the very fabric of space and time itself. Neutron stars are far more than just the endpoint of a massive star's life. They are key pieces of the cosmic puzzle, pointing to deeper, unresolved mysteries in the universe. With each new discovery, we move closer to understanding how the universe works at its most fundamental level, and what these stellar remnants can tell us about the origins and evolution of the cosmos. When a massive star reaches the end of its life, its core collapses under its own gravity, leading to the formation of one of the most mysterious objects in the universe, a black hole. These extraordinary objects are the result of the most extreme conditions imaginable, where matter is crushed to an infinite density within a region of space so small that not even light can escape. The creation of a black hole marks the end of a star's existence, but in many ways, it marks the beginning of a new chapter in our understanding of space and time. The process of black hole formation begins when a high-mass star exhausts its nuclear fuel. The core of the star becomes unstable and collapses under its own gravity, creating an incredibly dense singularity. The outer layers of the star are expelled in a massive explosion called a supernova. Once the core has collapsed, it forms a region known as the event horizon, the boundary beyond which nothing can escape, not even light. The event horizon is the defining feature of a black hole, marking the point where gravity becomes so strong that it warps space-time itself. At the heart of this process is the intense gravitational pull that shapes the very nature of a black hole. The idea that gravity can warp space-time was first introduced by Albert Einstein in his theory of general relativity. According to general relativity, mass and energy curve the fabric of space-time, creating what we perceive as gravity. In the case of a black hole, this warping is so extreme that space and time become intertwined and distorted, creating a region where the laws of physics as we understand them break down. The concept of black holes has fascinated scientists for decades, and many theoretical physicists have proposed groundbreaking ideas about the nature of black holes, suggesting that they may not just be remnants of stars but potentially gateways to other dimensions or alternate universes. One such idea comes from Roger Penrose, a renowned physicist who introduced the concept of the cosmic censorship conjecture. Penrose's conjecture posits that any singularity, such as the one at the center of a black hole, is always hidden behind an event horizon, preventing it from being observed directly. In essence, Penrose suggested that nature censors the singularity, protecting us from the infinite density and the breakdown of space-time that lies within. While the cosmic censorship conjecture suggests that black holes are not windows into the heart of the universe's most extreme forces, it raises an intriguing question. Could black holes actually be more than just remnants of stars? Could they be the doors to something entirely new? Perhaps even gateways to unknown dimensions or parallel universes? This idea has captured the imagination of many physicists, including David Finkelstein, who proposed an intriguing hypothesis about the nature of black holes and their potential to represent portals to alternate universes. Finkelstein's work focused on the topology of space-time, the study of the properties of space that remain unchanged under continuous transformations. He suggested that the singularity at the center of a black hole might not be a point of infinite density, but rather a doorway, where matter and energy could pass through to another universe. According to Finkelstein, the collapse of matter in a black hole could represent the birth of a new region of space-time, potentially giving rise to an entirely separate universe with its own set of physical laws. This idea challenges our conventional understanding of black holes and their role in the universe. If black holes are indeed gateways to other universes, they could fundamentally change our view of the cosmos. They would no longer be seen as just regions of space, where gravity is too strong for anything to escape, but as potential links to alternate realms of existence. The implications of such a theory are profound, as it suggests that the universe we see around us might be only one of many, with black holes serving as the bridges between these parallel worlds. Theories about black holes and their connection to alternate universes have been further explored by Max Tegmark, a physicist who is known for his work on the multiverse. Tegmark's multiverse theory proposes that our universe is just one of many, each with its own set of physical laws. According to Tegmark, black holes could be connected to other universes within this multiverse. The event horizon of a black hole might not just be a boundary beyond which nothing can escape. It could be a boundary between different universes, each with its own distinct set of laws governing space, time, and matter. Tegmark's ideas build on the idea that black holes could serve as conduits between these parallel universes. Instead of being isolated regions of space, black holes might be the key to unlocking the secrets of a larger multiverse, one in which the laws of physics are not uniform across all realms. This theory opens up a host of fascinating possibilities, including the idea that the universe we live in might be just one bubble in an ever-expanding foam of universes, each with its own version of reality. The speculative nature of these theories has sparked heated debates among physicists and cosmologists. While the notion of black holes as gateways to other universes is still purely theoretical, it highlights the deep mysteries that black holes present to us. What lies inside a black hole? Is it a point of infinite density, or is it a doorway to another universe? And if black holes are connected to alternate universes, what does that say about the very nature of reality itself? These questions have the potential to reshape our understanding of the universe and challenge the foundations of physics. The study of black holes and their role in the multiverse could provide the key to unlocking some of the most profound mysteries in science. As our understanding of black holes evolves, we may find that these enigmatic objects are not just the remnants of dead stars, but the keys to understanding the very fabric of reality. In the coming years, advancements in technology and our understanding of quantum mechanics, general relativity and gravitational waves may allow us to probe the nature of black holes in ways we never thought possible. Instruments like the Laser Interferometer, Gravitational Wave Observatory, LIGO, and the Event Horizon Telescope, which captured the first image of a black hole's event horizon in 2019, may offer new insights into the true nature of these mysterious objects. As we continue to explore the cosmos, black holes could provide the answers to some of the most profound questions about the universe, including the possibility that they are not just the end of space-time, but the beginning of something entirely new. The concept of black holes as portals to other universes challenges our traditional understanding of space, time, and reality. While much of this remains speculative, the idea that black holes could connect us to alternate realms offers a tantalizing glimpse into the unknown. As we push the boundaries of our knowledge, the study of black holes will undoubtedly continue to be one of the most exciting and mysterious frontiers in modern physics, offering new perspectives on the nature of the cosmos and the potential for hidden dimensions beyond our own. When we think about black holes, the first thing that often comes to mind is the event horizon, the boundary beyond which nothing can escape, not even light. But what happens beyond that point? What lies inside a black hole? The truth is, no one knows for sure, but we have some fascinating theories that help us explore this unknown region. The heart of a black hole, the singularity, is where our current understanding of physics begins to break down and the mysteries only deepen. The singularity is the point at the center of a black hole where gravity is so intense that it compresses all matter into an infinitely small and dense point. The density of the singularity is thought to be infinite, which raises fundamental questions about how space, time, and matter behave under such extreme conditions. In fact, the concept of infinite density challenges the very foundations of physics. According to the theory of general relativity, which describes the behavior of large-scale objects like stars and galaxies, this infinite density at the singularity creates a paradox that has baffled scientists for decades. The laws of physics, as we understand them, simply cannot handle such extreme conditions, leading to the realization that something deeper is needed to explain the behavior inside a black hole. One of the most important contributions to our understanding of black holes and their singularities comes from Roger Penrose. In the 1960s, Penrose formulated what is known as the singularity theorem, which posits that under the right conditions, the collapse of a massive star will result in the formation of a singularity. Penrose's work suggests that a black hole's core could indeed contain infinite density, where the gravitational pull is so strong that space-time itself is curved infinitely. This idea challenges our classical understanding of physics because it suggests that the usual rules we use to describe the universe no longer apply at the singularity. This realization points to the need for a new theory that can unite general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which governs the smallest particles in the universe. As we venture closer to a black hole's event horizon, another phenomenon begins to take hold: spaghettification. This term, though somewhat playful, describes a very real and very violent process that occurs when an object gets too close to the black hole. The immense gravitational forces near the event horizon stretch objects in the direction of the black hole and compress them in the perpendicular direction, like a piece of spaghetti being pulled apart. This stretching effect becomes more pronounced as an object approaches the singularity, where the gravitational gradient, the difference in gravitational pull between 2 points, becomes so steep that it tears the object apart at the atomic level. While spaghettification is something that could only be observed near a black hole, it offers a glimpse into the bizarre and extreme forces at work in these regions. At the event horizon, things become even stranger. Time itself slows down relative to an outside observer. As an object approaches the black hole's event horizon, from the perspective of someone watching from a safe distance, time appears to stretch and slow, making it seem as if the object is frozen in place. For the object falling into the black hole, however, it continues its descent, experiencing time normally, even as the rest of the universe speeds up relative to it. This time dilation is a direct result of the warping of space-time near a black hole, as predicted by Albert Einstein's theory of general relativity. While this concept of time slowing down at the event horizon is well understood, the deeper mysteries of what happens inside the black hole remain elusive. Stephen Hawking, one of the most influential physicists of the 20th century, brought a new perspective to the study of black holes with his groundbreaking work on black hole thermodynamics. In the 1970s, Hawking proposed that black holes are not entirely black, but rather emit a faint radiation, now known as Hawking radiation. This radiation arises due to quantum effects near the event horizon, where particles and antiparticles spontaneously pop in and out of existence. Normally these pairs of particles would annihilate each other, but near the event horizon, one particle can be sucked into the black hole, while the other escapes as radiation. Hawking's theory suggested that black holes might eventually lose mass and energy through this radiation, and if they don't accumulate enough mass, they could even eventually evaporate. Hawking's work also introduced what is now known as the information paradox. According to the principles of quantum mechanics, information about a system should never be lost, but black holes seem to violate this rule. When matter or energy falls into a black hole, it seems to be lost forever, and thus any information about it is destroyed. This paradox has led to significant debates in theoretical physics, as it suggests that our understanding of the fundamental laws of the universe is incomplete. The information paradox challenges our ability to reconcile the principles of quantum mechanics with general relativity, and it remains one of the biggest unresolved questions in modern physics. While much of the work on black holes centers around understanding the singularity and the event horizon, the true nature of these objects also ties into larger questions about the fabric of space-time itself. The intersection of general relativity and quantum mechanics is one of the most active areas of research in physics today. The quest for a theory of quantum gravity, which would unite the two, is essential for understanding black holes and the fundamental workings of the universe. Black holes represent a place where both the effects of gravity and the laws of quantum mechanics must be considered together. This combination of physics could potentially open new doors for understanding not just black holes, but the nature of space and time on the smallest and largest scales. Many of the ideas surrounding black holes, especially those concerning quantum effect, are still highly speculative. However, as research progresses, and as new technologies and techniques are developed, we may soon be able to probe the nature of black holes in ways that were once thought impossible. Instruments like the Event Horizon Telescope, which captured the first ever image of a black hole's event horizon in 2019, allow scientists to study black holes more directly than ever before. These advances could provide the key to unlocking the deepest mysteries of space and time, helping us to understand what happens inside a black hole and how it might reveal hidden aspects of the universe. The idea of the singularity at the heart of a black hole challenges our understanding of physics and forces us to confront the limits of our current theories. While we may never be able to peer into the heart of a black hole, the study of these enigmatic objects continues to push the boundaries of science and our understanding of the universe. As we delve deeper into the nature of black holes, we are not just exploring the endpoints of stars, but the fundamental structure of space and time itself, and the mysteries that lie beyond the horizon. When a star reaches the end of its life, it doesn't just fade into oblivion. Instead, it leaves behind remnants that continue to shape the universe long after the star itself has gone. These remnants, white dwarfs, neutron stars, and black holes, are some of the most fascinating and enigmatic objects in the cosmos. Though the star itself may no longer shine, the impact of its death can still be felt across vast stretches of space and time. The fate of stellar remnants begins with the death of the star. For stars with masses similar to our Sun, the end is marked by the shedding of outer layers, forming a glowing shell of gas and dust known as a planetary nebula. What remains of the star is the core, which becomes a white dwarf. White dwarfs are incredibly dense objects. Despite their size being comparable to Earth's, they can have a mass equal to that of the Sun. These stellar remnants are the final stage in the life of low to medium mass stars, and while they no longer engage in fusion, they will continue to cool and fade over billions of years. However, for more massive stars, their fate is far more dramatic. Once these stars reach the end of their fuel, they undergo a supernova explosion, an event that can outshine an entire galaxy for a brief moment. The remnants of these massive stars form neutron stars, objects that are even denser than white dwarfs, where neutrons are packed tightly together under extreme pressure. If the star is massive enough, the collapse continues, and the result is the formation of a black hole, a region of space where gravity is so intense that not even light can escape. While these stellar remnants may seem like the quiet end of a star's journey, they are far from inactive. Instead, they play a vital role in shaping the future of the universe. White dwarfs, neutron stars, and black holes continue to exert gravitational influence on their surroundings, affecting the orbits of nearby objects and the behavior of material in their vicinity. The material expelled during a supernova can enrich the surrounding space with heavy elements, contributing to the formation of new stars, planets, and even life itself. The long-term fate of the universe is intimately tied to the evolution and death of stars. As stars exhaust their nuclear fuel and die, they contribute to what is known as the heat death of the universe. The heat death is a theoretical scenario in which the universe reaches a state of maximum entropy, where all energy is evenly distributed and no thermodynamic work can be done. In this state, stars would no longer be able to shine, and the universe would grow cold and dark. The death of stars and the formation of their remnants play a crucial role in this process. As white dwarfs, neutron stars, and black holes continue to cool over billions of years, they will gradually contribute to the overall entropy of the universe. This process, combined with the ongoing expansion of the universe, means that over time the cosmos will become less and less energetic. The heat death is still far off, billions of years in the future, but it represents the eventual fate of a universe that is slowly running out of usable energy. Stars also play a pivotal role in shaping the structure of the universe. The formation of galaxies, star clusters, and even planetary systems is driven by the birth, death, and evolution of stars. As stars form from molecular clouds of gas and dust, they set the stage for the creation of the very structures that make up the universe. When stars die, they scatter their material into space, enriching the interstellar medium with heavier elements. This material then becomes the raw material for the next generation of stars and planets. In addition to their role in cosmic evolution, stellar remnants also provide insight into the nature of the universe itself. Black holes, for example, challenge our understanding of space and time. The intense gravitational fields around black holes cause space-time to warp, creating a region where the laws of physics as we know them break down. These objects are key to exploring the relationship between general relativity and quantum mechanics, as the extreme conditions inside a black hole may offer clues to a unified theory of gravity. As the universe continues to expand, stars will continue to evolve and die, leaving behind their remnants. This process, while it may seem like an end, is actually part of an ongoing cycle of creation and destruction. As stars die and their remnants cool, they will eventually become part of the cosmic backdrop, contributing to the ever-expanding universe in subtle and complex ways. The expansion of the universe itself is another factor in the fate of stars and their remnants. As space stretches, galaxies move farther apart, and the density of the universe decreases. Stars will continue to form in the early stages of the universe's life, but as time goes on, the raw material for new stars will become less abundant. Eventually, star formation will slow, and the universe will be left with the remnants of once active stars. These objects will continue to exist for eons, but they will no longer be able to produce new stars or support the processes that sustain life. In the distant future, the universe will be dominated by these stellar remnants, cold, dark, and gradually fading. The white dwarfs, neutron stars, and black holes will remain as the last witnesses to the vibrant stars that once lit up the cosmos. And yet, despite their gradual cooling and eventual decay, these remnants will continue to shape the universe's evolution, marking the end of one era and the beginning of another. In this future, there will be no more supernovae, no more new stars forming, and no more stellar explosions to enrich the interstellar medium. The universe will be a quieter, dimmer place, where the remnants of dead stars drift through the vastness of space, continuing to exert their gravitational influence. These objects, though no longer active, will serve as the final remnants of a once luminous cosmos, their slow cooling marking the passage of time in a universe that will eventually reach the end of its thermodynamic life. The fate of stellar remnants is inextricably linked to the future of the universe. As stars die and their remnants evolve, they shape the ultimate destiny of the cosmos. The death of a star is not just the end of a single life, but a crucial step in the ongoing evolution of the universe. From the birth of new stars to the eventual cooling and fading of black holes, these remnants will continue to influence the universe for billions of years to come, leaving an indelible mark on the fabric of space-time itself. Stars are the architects of the universe, shaping not only the galaxies they inhabit, but also the very elements that form the building blocks of life. From their birth in stellar nurseries to their ultimate death in spectacular explosions, stars play a pivotal role in the ongoing evolution of the cosmos. Their life cycles are intrinsically linked to the birth, development, and eventual fate of galaxies, star clusters, and the universe itself. Understanding the role of stars in cosmic evolution helps us appreciate how intricately connected everything in the universe truly is. When a star forms, it doesn't just create light and heat, it also contributes to the complex web of matter that makes up the universe. The process of stellar formation begins when gas and dust in molecular clouds collapse under their own gravity, eventually igniting nuclear fusion in the star's core. This fusion process, which powers stars, is where the magic of cosmic creation begins. As stars burn hydrogen into helium, they create lighter elements, but they are also factories for heavier elements, such as carbon, oxygen, and iron, which are essential for the formation of planets and, eventually, life. The fusion of elements inside stars serves as a cosmic assembly line, churning out the raw materials that make up the universe. These elements are not just confined to the stars themselves, they are distributed across space when stars die. The death of a star is often as significant as its life, especially for high-mass stars that end their existence in dramatic supernova explosions. When these stars explode, they scatter the heavier elements they have created throughout space, enriching the interstellar medium. This material, made of everything from carbon to gold, becomes the foundation for future generations of stars and planets. Without these stellar explosions, the universe would lack the building blocks necessary for the formation of rocky planets, the development of life, and the very matter that makes up our bodies. Supernovae, the explosive deaths of massive stars, are among the most important events in this process. When a star explodes in a supernova, it doesn't just shine brightly for a brief moment. It leaves behind a rich array of heavy elements that spread out across space. These elements, created in the heart of the star during its lifetime, are scattered into the surrounding gas and dust, providing the raw material for the formation of new stars and planets. Supernovae are responsible for creating many of the heavy elements that we find on Earth and throughout the universe. For example, Elements like iron, nickel, and gold are all produced in the intense conditions of supernovae. In this way, stars through their lives and their deaths act as cosmic factories that create the elements necessary for life and shape the structure of the universe. Stars also play an essential role in shaping the dynamics of their host galaxies. The formation and death of stars influence the movement of galaxies and the formation of new stars. In the early stages of a galaxy's life, star formation occurs rapidly as gas and dust collapse under gravity to create new stars. Over time, the rate of star formation slows down, but the stars that remain continue to affect the galaxy's evolution. The balance between the gravitational pull of stars and the energy they emit can shape the galaxy's structure, determining whether it remains a spiral galaxy like our Milky Way or evolves into an elliptical or irregular galaxy. The feedback from supernovae, stellar winds, and other energetic events also plays a significant role in regulating star formation in galaxies. For instance, the energy released by a supernova can trigger the collapse of nearby gas clouds, leading to the formation of new stars. Similarly, the intense radiation from young, hot stars can prevent gas from collapsing into new stars, thus regulating the overall star formation rate in a galaxy. As stars live and die, they contribute to the ongoing evolution of galaxies, star clusters, and the universe. When a star reaches the end of its life and becomes a white dwarf, neutron star, or black hole, it continues to influence the dynamics of its surroundings. White dwarfs, which are the remnants of low to medium mass stars, gradually cool and fade over billions of years, but their gravitational influence continues to affect nearby stars and planets. Neutron stars, the remnants of massive stars, can have incredibly strong magnetic fields and emit radiation in the form of pulsars, influencing the environment around them. Black holes, the most extreme of all stellar remnants, warp spacetime itself and can even affect the orbits of stars and gas in their vicinity. The presence of these remnants can impact the formation of new stars and the overall evolution of their host galaxies. While stars may appear to be individual objects burning brightly in the sky, their life cycles are deeply connected to the larger processes that shape the universe. Their creation of elements, influence on galaxies, and contribution to the cosmic balance all play a vital role in shaping the universe's structure and future. As the universe continues to expand, the fate of stars will continue to have a profound impact on the cosmic landscape. Looking into the future, the death of stars will lead to the gradual cooling and dimming of the universe. Over billions of years, as stars burn out and their remnants cool, the universe will slowly approach what is known as the heat death. In this state, the universe will have reached maximum entropy, with energy spread out so evenly that no thermodynamic work can be done. Stars will no longer shine, and galaxies will be left with only remnants of their former selves. White dwarfs, neutron stars, and black holes, slowly fading into the cold, dark expanse of space. This slow process, though distant, marks the eventual end of the universe's capacity to support life and energy. However, the influence of stars will continue for billions of years to come. Their life cycles are part of a cosmic rhythm, where new stars are born from the remnants of old ones, and galaxies evolve as stars live, die, and transform. The energy released by stars over their lifetimes shapes the interstellar medium, promotes the formation of new stars, and drives the evolution of galaxies. As the universe continues to expand and evolve, the role of stars in its dynamic structure remains crucial. From the smallest red dwarf to the most massive supergiant, stars are the engines that power the universe, and their lives and deaths leave an indelible mark on everything that follows. In this sense, stars are not just part of the universe, they are integral to its ongoing story, constantly shaping and reshaping the cosmic tapestry. The philosophical implications of stars' lives and deaths also invite us to consider our own place in the universe. Stars are the creators of the elements that make up our bodies and our world. They are the catalysts for life, the engines of cosmic evolution. As we look to the stars, we're not just gazing at distant objects in the sky, but at the very forces that have shaped the universe for billions of years and will continue to do so long after we are gone. The life cycles of stars remind us of the impermanence of all things, yet they also speak to the resilience and continuity of the universe. The death of stars is not an end, but a transformation, and in this transformation, the universe continues to evolve, creating new stars, new galaxies, and perhaps new forms of life. To witness the death of a star is to glimpse one of the most dramatic and energetic events in the universe. It is a cosmic spectacle that can illuminate the night sky, outshining entire galaxies for brief moments. But how do astronomers observe these elusive events? Stars are, after all, incredibly far away, and their deaths unfold over timescales that stretch far beyond a human lifetime. The answer lies in the remarkable tools and technologies that allow us to peer deep into the cosmos, capturing the light from these distant explosions and studying the remnants they leave behind. The development of telescopes has revolutionized our understanding of the universe. These instruments allow us to gather and focus light from distant stars, planets, and galaxies, providing a window into the far reaches of space. In the case of observing star deaths, telescopes are indispensable. Whether it's the violent explosion of a supernova or the slow fading of a white dwarf, telescopes help us understand these events in real time and in great detail. One of the most important tools in modern astronomy is the Hubble Space Telescope, which has revolutionized our ability to observe the universe since its launch in 1990. Positioned far above Earth's atmosphere, Hubble's location in space allows it to avoid the distortions caused by the atmosphere, which can blur the images taken by ground-based telescopes. Hubble has provided breathtaking images of starbirths and deaths, capturing the explosive beauty of supernova remnants and the delicate, glowing remnants of dying stars in planetary nebulae. Hubble's ability to capture high-resolution images across multiple wavelengths of light, visible, ultraviolet, and infrared, has made it a critical tool for studying stellar death. By observing stars in different wavelengths, astronomers can learn about the different stages of a star's life cycle. For instance, the fading glow of a supernova's remnant can be studied in infrared, where cooler objects emit light, allowing us to study the cooler, expanding gas and dust that is left behind after the explosion. The ultraviolet light emitted by dying stars reveals more about their intense energy output, helping scientists understand the last stages of stellar evolution. While space telescopes like Hubble have transformed our understanding of stellar death, ground-based observatories continue to play a vital role as well. These observatories, often located in remote locations like mountaintops, provide powerful views of the sky, albeit through the atmosphere. Advances in technology have helped overcome some of the challenges posed by Earth's atmosphere, with instruments like adaptive optics helping to correct the distortions caused by atmospheric turbulence. This allows astronomers to achieve sharper images, rivaling those from space telescopes, even from the ground. One of the most important tools for observing the death of stars in the infrared and radio wavelengths is the Very Large Telescope, VLT, in Chile. Located in the Atacama Desert, the VLT is one of the most advanced ground-based observatories in the world. It consists of 4 large telescopes, each capable of observing distant stars, supernovae, and other stellar phenomena with remarkable clarity. With the help of the VLT and similar observatories, astronomers have been able to observe supernovae in their aftermath, learning about the shock waves and the heavy elements created in the explosions. In addition to optical telescopes, astronomers also use other specialized instruments to study star deaths. For example, gravitational wave observatories like the Laser Interferometer, Gravitational Wave Observatory, LIGO, have made groundbreaking discoveries in recent years. Gravitational waves are ripples in space-time caused by massive objects like black holes or neutron stars colliding or merging. These waves carry information about the most violent and energetic processes in the universe, including the deaths of stars. When 2 neutron stars collide and explode in a supernova, or when a black hole forms, the resulting gravitational waves can be detected on Earth, providing valuable data about these otherwise invisible events. The study of star deaths is essential for understanding the past, present, and future of the universe. Supernovae, for instance, are responsible for creating many of the elements that make up planets, stars, and even life itself. Without these violent explosions, the universe would lack the heavy elements necessary for the formation of rocky planets like Earth. By studying how stars die, we learn not just about the stars themselves, but about the very nature of the universe and the processes that shape it. Moreover, the study of stellar death helps us understand the long-term evolution of galaxies. Stars influence the dynamics of their host galaxies in many ways, from their formation to their death, and the creation of new stars. As stars explode in supernovae, they release vast amounts of energy and heavy elements into their surroundings, triggering the formation of new stars. These cycles of birth and death have shaped the structure of galaxies over billions of years. By observing how stars die, we gain insights into the future evolution of galaxies, helping us understand the larger cosmic picture. The ability to observe star deaths also brings with it philosophical and existential implications. As we study the life cycles of stars, we are reminded of the impermanence of all things. Stars, like all living things, are born, live, and eventually die. Their deaths, though violent, are not final. Instead, they are part of an ongoing process of transformation, where the matter that once made up a star is recycled into new stars, planets, and even life. In this way, the death of a star is not an end, but a part of the larger cycle of creation and destruction that defines the universe. The study of stellar death also speaks to a deeper human curiosity about the cosmos. We have always been fascinated by the stars, looking up at the night sky and wondering about their nature and their fate. Our desire to understand how stars are born and die is a reflection of our larger desire to understand the universe itself. By studying stars, we learn not only about their lives, but about the origins of the universe, the laws of physics, and the forces that govern all of existence. It is through the death of stars that we gain some of the clearest glimpses into the workings of the universe, and as our tools and technologies continue to improve, we will undoubtedly uncover even more secrets about the stars and their role in shaping the cosmos. The study of star deaths is a vital part of the ongoing exploration of the universe. With the help of space telescopes like Hubble, ground-based observatories like the VLT, and cutting-edge technologies like gravitational wave detectors, we are learning more about stellar evolution and the forces that govern the universe. These advances in technology continue to deepen our understanding of the cosmos, bringing us closer to the mysteries of the universe's past, present, and future. And as we continue to explore the stars, we continue to satisfy our deepest curiosity about the nature of existence itself. When we gaze up at the night sky, we often marvel at the stars, those distant points of light that have shone for millions, sometimes billions, of years. But there's more to the stars than just their beauty. In fact, our very existence is deeply tied to their life cycles. The death of stars, often violent and dramatic, plays a crucial role in shaping the universe around us, and ultimately in shaping life itself. The elements that make up our bodies, the planets, and even the life-sustaining environment on Earth were forged in the cores of stars long before our solar system came into being. Stars are cosmic furnaces where elements are created through the process of nuclear fusion. In the early stages of a star's life, hydrogen atoms fuse to form helium, releasing immense amounts of energy. As stars age and burn through their fuel, they begin fusing heavier elements, carbon, oxygen, and, in the case of massive stars, even elements like iron. When these stars eventually die, particularly in dramatic events like supernovae, they scatter these heavy elements into space, enriching the interstellar medium. This material, composed of elements like carbon, nitrogen, and oxygen, is essential for life. Over time, it gathers into new stars, planets, and eventually life forms. Our bodies, for instance, are made up of elements that were once created in the hearts of ancient stars. Carbon, the building block of life, was formed in the cores of stars long before the Earth even existed. The oxygen we breathe and the nitrogen in our atmosphere were also created through stellar processes. Even the gold and iron found in the Earth's crust were forged in the explosive deaths of stars. These elements were spread out across space in the aftermath of supernovae, eventually coalescing into the material that formed our planet and everything on it. In this sense, we are stardust, quite literally. We owe our existence to the life and death of stars. Without the explosions of dying stars, Earth would not have the essential elements needed for life. And it's not just our planet that benefits. Stars are the architects of the entire universe. Their deaths give birth to new stars, galaxies, and even black holes. Each generation of stars builds upon the last, creating a constantly evolving cosmic tapestry. But the death of stars also has broader philosophical and existential implications. The cycles of birth and death that we observe in the stars mirror the cycles of life here on Earth. Just as stars are born, live, and eventually die, so too are the life forms that inhabit this planet. There's a certain poetic symmetry in this cosmic process. The death of stars not only enables the creation of life, but also reminds us of the transient nature of existence. Everything in the universe is in a constant state of flux, from the tiniest atoms to the largest galaxies. The inevitable death of stars and the eventual fading of their remnants serve as a reminder that nothing in the universe lasts forever. But what does the future hold for humanity in relation to the death of stars? As the Sun, a relatively low-mass star, enters its later stages of life, it will expand into a red giant, eventually engulfing the Earth and causing the planet to become uninhabitable. This event, which is still billions of years away, will mark the end of life on Earth as we know it. However, the death of the Sun will not be the end of the universe. Even as our Sun fades, the universe will continue to evolve, with new stars being born from the remnants of older ones. The cycle of life, death, and rebirth will carry on for billions of years to come. On a larger scale, the eventual death of stars will lead to the cooling of the universe, as all the energy created by stars is gradually used up. The concept of heat death suggests that in the distant future the universe will reach a state of maximum entropy, where all the energy is evenly spread out, and no thermodynamic work can be done. At that point, stars will no longer shine, and the universe will be cold and dark. This scenario may seem bleak, but it's important to remember that this is an incredibly long-term outcome. For now, stars are still being born, living and dying, shaping the universe in the process. Human curiosity has always been driven by a desire to understand the universe, and our exploration of the cosmos is inextricably linked to our understanding of stars. As we look to the stars, we seek to understand our place in the universe and the forces that govern it. The study of stars, from their birth in nebulae to their explosive deaths as supernovae, allows us to trace the history of the cosmos and our own origins. By understanding the life cycles of stars, we can better understand the evolution of galaxies, the formation of planets, and the conditions that allow life to exist. The curiosity that drives our exploration of space is not just about gathering knowledge. It's about understanding the fundamental processes that shape everything around us. Stars are more than just points of light in the night sky. They are the engines of creation, the sources of the elements that make up our world, and the driving force behind the ongoing evolution of the universe. By studying the death of stars, we gain insights into the past, present, and future of the cosmos, and perhaps even into the nature of life itself. The death of stars also has a profound impact on how we view the future of humanity. As we continue to explore space, we're not just studying the stars, we're learning about our own future. Understanding the eventual fate of the Sun and the Earth helps us to reflect on our place in the cosmos and consider the long-term survival of our species. While the death of the Sun is still billions of years away, our exploration of space and the search for habitable planets around other stars may one day allow us to find a new home, ensuring the continuation of human life in the distant future. Ultimately, the life and death of stars are interconnected with the existence of life on Earth. Without stars, there would be no planets, no life, and no possibility for consciousness to contemplate the mysteries of the universe. As we look up at the stars, we are reminded of our shared cosmic history and the fact that we are part of a much larger cycle of creation and destruction. The death of stars is not an end, but a transition, one that creates the conditions for new life, new stars, and new worlds. And in this cycle, we find a deep connection between the stars and ourselves, one that transcends time and space. The study of stellar evolution has come a long way since astronomers first began to ponder the lives of stars. From the birth of stars in nebulae to their eventual deaths, whether in the form of white dwarfs, neutron stars, or supernovae, we've gained a deep understanding of how stars evolve and die. Yet, despite centuries of observation and research, many fundamental questions remain unanswered. These gaps in our knowledge continue to push the boundaries of astrophysics, prompting scientists to search for new ways to study stars and their role in the universe. One of the most pressing unanswered questions concerns the connection between quantum mechanics and stellar phenomena. While we have made significant strides in understanding the macroscopic aspects of stellar evolution, the microscopic processes, those governed by quantum mechanics, remain much more elusive. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, is fundamentally different from the classical physics that governs the behavior of stars on a larger scale. The true challenge lies in uniting these two realms. How can we explain the behavior of stellar cores, where both quantum effects and the force of gravity are at play, in a single unified theory? Brian Greene, a theoretical physicist best known for his work on string theory, has explored ideas that could bridge the gap between quantum mechanics and astrophysics. Greene's work suggests that the fundamental nature of spacetime itself may be influenced by quantum mechanics in ways we have yet to fully understand. For example, in the cores of stars where gravity is immense and nuclear fusion takes place, quantum effects may play a crucial role in determining how fusion reactions unfold. The study of these extreme environments may help us unlock a deeper understanding of the fabric of spacetime and lead us to a unified theory of quantum gravity. Similarly, Juan Maldacena, another leading physicist, has contributed significantly to our understanding of quantum gravity with his ideas on the holographic principle. This principle suggests that the behavior of a three-dimensional space can be described in terms of two-dimensional information, encoded on its boundary. In the context of black holes, Maldacena's work could help us understand how quantum mechanics applies to regions of space where gravity is so strong that it warps spacetime itself. His theories could provide insights into what happens inside black holes and offer clues about how stars die and what lies beyond the event horizon. As we continue to search for answers to these fundamental questions, the next frontier in astrophysics involves the exploration of stellar death in new and exciting ways. One of the most promising advancements in recent years is the detection of gravitational waves, ripples in spacetime caused by the movement of massive objects. The collision and merger of black holes and neutron stars, for example, generate these waves, providing scientists with a new way to study the violent death throes of stars. Gravitational wave observatories like LIGO and Virgo have already detected several mergers of black holes and neutron stars, opening up a new window into the study of stellar evolution. These discoveries have confirmed many predictions made by Albert Einstein over a century ago, but they have also raised new questions. For instance, how exactly do black holes and neutron stars form, and what role does stellar mass play in determining whether a star becomes a black hole or a neutron star? As gravitational wave detectors become more sensitive, we will likely uncover even more about these mysterious objects and the violent events that lead to their formation. In addition to gravitational waves, future space missions will play a crucial role in advancing our understanding of stellar death. Instruments like the James Webb Space Telescope, set to launch in the near future, are designed to capture the faint light emitted by the most distant stars and galaxies, including those in the final stages of their evolution. Webb's infrared capabilities will allow us to peer deeper into space than ever before, giving us a clearer picture of how stars form and die in the early universe. This will provide valuable insights into the history of star formation and the factors that influence a star's ultimate fate. One of the most exciting aspects of the future of stellar science is the potential for groundbreaking discoveries in the coming decades. As our technology improves and our theoretical models evolve, we may finally begin to answer some of the most profound questions about the nature of stars and their role in shaping the universe. The death of stars, once seen as a natural and predictable process, may hold deeper mysteries that we have yet to unravel. Are there undiscovered processes at play during a star's death? What happens in the final moments before a star collapses into a black hole or explodes in a supernova? How do quantum mechanics and gravity interact at the most extreme levels, inside the cores of dying stars and black holes? These questions open doors to entirely new realms of physics. As we continue to study stars and their death throes, we may uncover new aspects of the universe that challenge our current understanding. In doing so, we not only learn more about the stars themselves, but also about the fundamental forces that govern the universe as a whole. The quest for knowledge about the life and death of stars is not just about answering scientific questions. It is about understanding our place in the cosmos. Stars are not only the engines of creation, responsible for the elements that make up our planet and our bodies, but they also serve as a reminder of the impermanence of all things. Just as stars are born, burn brightly, and eventually fade, so too do the civilizations that arise in their light. Our curiosity about stars and their death is a reflection of our broader quest to understand the universe and our own place within it. Looking ahead, the future of stellar science promises to be filled with discovery. New telescopes, more sensitive gravitational wave detectors, and advances in theoretical physics will provide answers to questions that have long eluded us. The evolution and death of stars may hold the key to unlocking some of the deepest mysteries of the universe, from the nature of dark matter and dark energy to the behavior of space-time itself. With each new discovery, we take one step closer to understanding the cosmos and the fundamental processes that govern it, and perhaps, in doing so, we will also come to understand the forces that shape our own existence and our place in the grand unfolding story of the universe. As we have explored throughout this journey, stars are not just celestial bodies that light up the night sky. They are the very engines of creation in the universe, from their birth in vast cold molecular clouds to their dramatic deaths in supernovae or their quiet fades into white dwarfs. The life cycle of stars is both awe-inspiring and humbling. Stars forge the elements that make up planets, life, and everything in between, shaping the cosmos in ways we're still discovering. Their deaths, far from being the end, are critical moments of cosmic transformation, scattering elements into space, allowing new stars to be born, and enriching the interstellar medium for future generations. The death of stars, with its many forms, whether it be the explosion of a supernova, the slow cooling of a white dwarf, or the gravitational collapse into a black hole, brings with it both creation and destruction. Through these processes, stars serve as both the creators and destroyers of the very elements that make up the universe, and thus our own existence. The profound connections between stellar life cycles and the broader evolution of galaxies, star clusters, and the universe remind us that everything in the cosmos is interconnected. Our understanding of star death not only informs us about the past and present of the universe, but also connects to broader themes of existence, time, and space. The cycles of birth and death that we observe in stars mirror the natural rhythms of the cosmos, and perhaps even life itself. As we reflect on these cosmic processes, we are reminded of the impermanence of all things, and yet in this impermanence we find the essence of creation, transformation, and continuity. Stars may burn brightly for a time, but their lives and deaths ensure the perpetuation of the universe's evolution. The death of stars is a powerful symbol of the infinite cycle of creation and destruction that governs the cosmos. As we contemplate the far future, we see that this cycle will continue for billions of years, with stars continually born, living and dying, shaping the universe and everything within it. And as we peer into the mysteries of the stars, we are not just looking at distant lights in the sky, but at the forces that shape our very existence. So, in the grand scheme of things, perhaps the story of star death is a reminder of the deep interconnection between the cosmos and ourselves, forever linked in the endless dance of creation.